Thank you for this very nice introduction. I feel a little inadequate, not having either a Nobel Prize or a field medal or anything like this. Not even being a mathematician, actually. I used to be an engineering student. I blew up a few things, which is why I switched to software. Okay, so not surprisingly, I'm going to talk about deep learning. I'm not assuming anything from the audience, so I'm going to try to kind of cater to the very diverse audience here, from people who've heard my talk half a dozen times, like Mark, over many different years, or and people who really don't know what deep learning or machine learning even is about. So let me start a little bit with the inspiration for artificial intelligence. And my first slide is actually not about AI, it's about flight. So there is artificial intelligence, and we get inspired by what we observe in nature the same way the pioneers of aviation got inspired by what they observe in nature for flight. And nature has been certainly an inspiration for flight, where the first pioneers of aviation tried to actually reproduce the flight of birds with flapping wings and wings that were shaped like bats and things like this. In fact, this airplane you see here at the bottom left is probably the first one to have taken off by itself under its own power in 1890, and it was shaped like a bat. It was completely uncontrollable. There was no tail, there was no stabilization, there was no idea of anything like this, but which is why you probably never heard of it. It flew for about 50 meters, about 20 meters altitude, and then kind of destroyed itself. So there was kind of a little bit of inspiration from biology, but probably too much inspiration from biology without really understanding the underlying principles. And it's only with a more systematic approach to engineering, in particular by the Wright brothers, that kind of flight became practical. And so this was sort of systematic exploration, building wind tunnels, experimenting with airfoils, experimenting with kites, with gliders, with models, etc. So there is kind of systematic engineering approaches to this, and the theory came later. So the theory of stability and a lot of aerodynamics actually came after people started building airplanes, because it became so interesting. So it's very often the case that people produce an artifact, and then the theory comes later. And it's a little bit the case with deep learning. I'll come to this in a minute. So can we be inspired by nature to build intelligent machines? And of course, it's an old idea, and it's kind of obvious. And so we can look at the brain. The brain has, the human brain has roughly 85 billion neurons. Each of those neurons is connected to something like 10,000 other neurons on average, between 1,000 and 10,000, sometimes more, sometimes 100,000. It weighs about 1.4 kilograms. It's actually a sheet. It's flat. It's about 2 millimeters thick. And if you kind of unroll it, it's about 2,500 square centimeters, with a ridiculously long series of wires that connect all those areas with each other. And it's very efficient. It consumes about 25 watts, which is about a tenth of what a typical PC would consume. A big PC. So one thing, though, that's very interesting about the brain is that pretty much every animal that has a brain can learn. Sometimes in sort of very, very simple ways, like this little slug here. But most of the time, they can learn amazing feats. And very often, without any supervision by another intelligent entity, they can learn by themselves. And it's a bit of a mystery how that occurs. And in fact, we haven't really completely unlocked this mystery. And a lot of the research today is how to make learning in machines more, as efficient as learning in animals. So in fact, the idea of kind of getting inspiration from the brain to build intelligent machines goes back to the 1940s. And perhaps the most striking demonstration of this was in the late 50s, a model called the Perceptron. So what the Perceptron it was not a computer. It was more like an analog computer. It was an electronic circuit, if you want, which is depicted here at the bottom. So you could show patterns here that were brightly lit, and then it would go to some sort of retina-like thing, and some sort of spaghetti plate here that they call the associative area, and then it would go to a bunch of what I call threshold elements. And what those threshold elements do, they do something very simple. They take the values that come in this case in the form of voltages, and they compute a weighted sum of those values, compare them to a threshold. If the weighted sum is above a threshold, the unit turns on. If it's below a threshold, it turns off. So mathematically, it's very simple. It's a weighted sum. These are the weights. These are the values. These are threshold or negative threshold, and you turn on if it's above the threshold, turn off if it's below. Each of those little module here that you see is one of those unit with a threshold. And the beauty of this is that the weights here could be trained so that the machine would perform a particular function. And each of those modules here that implements one of those weights is actually a potentiometer, the same kind that you have on your home amplifier, which would actually physically rotate and change the value of the, had a motor on it. And so it could rotate in one direction or the other, and that was the learning algorithm. Now we can replace this with about 3 lines of Python. But this was a massive machine. So how did this work? It's a very, very simple idea. And if you don't like math, don't look at this. But the idea is very simple. You have a collection of training samples. So this is kind of a way of, denoting this mathematically. So the inputs, the series of numbers that you show on the input, let's imagine that we want to recognize images. So an image is really an array of numbers where each pixel value is either 0 or 1, if it's white or black, let's say. And what this threshold unit is doing is computing a weighted sum of those pixels. Here we only represented 3 weights, so it's only taking into account those three pixels. And it's trying to figure out a combination of the weights here in such a way that is going to produce a large weighted sum when we show it the letter A, for example, and a smaller weighted sum when we show it the letter C, to take a random example. And the basic idea is very simple. You show an example, you tell it this is an A, therefore your output should be 1. So take every weight that has a pixel equal to 1 and increase their values. Okay, so that the weighted sum will increase a little bit. And then take all the weights whose input is 0, just don't do anything. If the input was -1, you would decrease the value of the weight so that the weighted sum would increase. If you show an example of an A and the output is already 1, you don't do anything. And if you show the letter C and you want and the machine says A, then you probably need to decrease the weighted sum, and you do this by decreasing all the weights whose incoming pixel is positive and vice versa for the negative. So it's a very simple idea. It's error corrective learning. You can express this in just a few lines, and you can write this way mathematically. That takes 1 line of Python, not 3. The 3 is for the loop, but. So, one particular weight is updated. You take the previous value of this weight and you compute the error. This is the difference between the output you want and the output you get out of the machine. So this is all +1s or -1s. So this whole difference here is either 0, +2, or -2. And then you multiply by the corresponding input. And this little, intuitive rule that I said, error correcting rule, is basically implemented by this one line. So that doesn't require any complicated math. In fact, a couple of years later, people showed that this was, even though Frank Rosenblatt, who came up with this idea kind of intuitively, later it was shown that it's actually a minimization of some function. So I'll get to this in a minute. But why is this inspired by biology? It's inspired by biology because in the brain, neurons learn by modifying the strength of the connections between them. So the brain is a network of many, many neurons. The neurons are connected by synapses, and the strength of those synapses change when we learn new things or when we remember things. And so that's derived from this idea, which goes back to the 40s and psychologists in the 40s. But mathematically, this is really minimizing an objective function. So think of the weights as, in this perceptron or this neural net, as knobs that adjust the input-output function of whatever it is you want to train. And there is an objective function that measures the discrepancy between what you get and what you want. And you average this over a number of training samples. You have a whole bunch of cars and airplanes and whatever it is that you want the machine to classify. And what you want is you want to adjust all those knobs in such a way that the average of this objective function, average over all the training samples, is as low as possible. That's called gradient descent. The particular type of gradient descent we implement with machine learning very often is called stochastic gradient descent. This sounds like it makes the whole thing more complicated, but actually makes it simpler. So basically, you take a sample, take an example here, and you do exactly what I described before. Measure the value of the objective function and just adjust the knobs just a little bit in some direction so that the objective function goes down, which means the output gets closer to the output you want. And you can sort of represent this, abstractly in sort of mathematics, where you have a function you want to optimize. It's got a minimum somewhere. Those lines, think of it as the lines of equal cost. So this is like a valley, where the altitude goes up as you move away from it. And you start from some random point, and then every sample you show, there is some sort of random direction a little bit, depending on the particular image that you show. And eventually the system kind of goes to the minimum of this function. Again, very simple math. It's very simple in principle to what people do when when you find a line that goes through points, you do curve fitting. Very simple. But what we'd like is do this for things that are more complicated than just points on the plane. We'd like to be able to, for example, classify images of cars from images of airplanes, or let's say chairs, but there's so many variability, so much variability in the appearance of chairs and cars and airplanes. How are we going to be able to do this? The principle is all going to be the same. Show an image. You want to turn the red light for cars. If the red light doesn't turn on, tweak all the knobs so that the red light increases in intensity, and perhaps the green light decreases in intensity. And then go to an airplane. You want the green light to turn on, tweak all the knobs so that the green light increases in intensity. And if you do this often enough with sufficiently many thousands of samples, and your machine is powerful enough, eventually the knobs will settle on the configuration where every car and every airplane is correctly classified. And the magic of machine learning is that even if you now show it an example it's never seen before, it will still have some likelihood of producing a correct classification. So to some extent, if you build those things properly, they will sort of abstract the notion of car and airplane and tables and chairs and things like that. Okay, so now the next question you have to ask, of course, is what do you put in this mysterious box here? And the answer has changed over the last couple decades. So the perceptron you could think of as something like this, where you show it an image, and then it goes to some sort of something that people in computer vision call a feature extractor, or in pattern recognition in general called a feature extractor. And that was generally built by hand. So you had to sort of engineer some sort of processing here that would turn this array of numbers, the pixel values in the image, into some sort of representation that a simple learning algorithm would be able to digest. And that's kind of the standard model of pattern recognition until very recently, until essentially the emergence of deep learning. Deep learning is the idea that instead of having a piece of the system that is handcrafted and another piece that's trainable, you kind of build the system as a cascade of multiple modules, all of which are trainable. And why is it interesting to have multiple modules, one after the other, that are all trainable? It's because of the question of hierarchy. I'll come back to this in a minute, but there's also a little bit of inspiration from biology here, where when you look at the architecture of the visual cortex, for example, the signal goes from the retina to the back of the brain, and then it kind of makes its way forward in sort of successive areas in the brain until the kind of object categories are represented. And so there is this notion of sort of multiple steps if you want to get to a recognition. So now the next question you can ask is, what are we going to put in those boxes? And again, if we get inspiration from this idea of neural nets, a very simple way of doing this, which people have been playing with for since the 50s, but more in the context of this idea of having multiple layers since the 80s, is the idea of multi-layer neural network. So what is a multi-layer neural network? It's basically a succession of layers, and you can take one particular unit in one of the layers of those machines, and one of those units basically computes a weighted sum of its inputs, and its inputs are the activations of the units on the previous layer, and the weights that it uses for the weighted sum are subject to learning, and then it compares this weighted sum to a threshold. If the threshold is below, if the weighted sum is below a threshold, it just outputs 0. And if it's above the threshold, it just outputs the weighted sum. So there is a nonlinear transformation here that we call a ReLU. It's just a half-wave rectification, or the max of x and 0, and it's got it's got this kind of response function here. So that's the weighted sum here, and that's the output of the unit. And you stack multiple layers of those units, each of which has its own coefficients for its own weighted sums. And what we're going to do is learn those coefficients or those weights. Think of this as those knobs that we're going to adjust. So mathematically, if you want to kind of abstract this a little bit, essentially you can think of an input, whether it's an image or a text or an audio signal or whatever else, whatever other natural signal, as kind of an array of numbers or a string of numbers, if you want, a vector or a two-dimensional array or three-dimensional array. But let's imagine that it's just a list of numbers, a vector. We take this vector, we multiply it by this matrix, which contains all the weights, all the coefficients, all those weighted sums, and what we get is another vector, and then we pass all the components of these vectors through this vector through this nonlinear function, and then repeat the process, pass it through a weight matrix again, multiply this vector by this weight matrix, pass the result through pointwise nonlinearity, et cetera, et cetera. And we can stack 20 layers, 50 layers of those sometimes. Okay, so how are we going to train this machine? Again, this is going to be this sort of error correcting type idea. But the trick here is going to be to figure out in which direction to change and by how much to change each of the coefficients so that the output gets closer to the output we want. And that's the main issue. And so the solution to this is surprisingly simple. And what's surprising is that it took until the mid-'80s, approximately, for the community to basically realize that it could work and to actually implement it to make it work. But the idea is very simple. Don't get scared by this. You can ignore this. It's a practical application of a very sophisticated mathematical concept called chain rule, which you learn in first year of college or perhaps in high school if you're in advanced courses. So the basic idea is very simple. When you have a network, which is basically a succession of functional blocks, so each of those blocks does either a matrix multiplication or applies this nonlinear function to each component. Let's take one block isolated inside this system. You can obviously easily compute the output of that block from its input. So if, for example, this is one of those linear blocks that multiplies by a matrix, the input is a vector, the parameter is a matrix, multiply this vector by this matrix, and you get the output vector. And those two vectors may have different dimensions. Okay, now what we need to do is, let's assume that we know for each component of this output, we know in which direction the cost would change if we tweak each of those components of this vector by a small amount. Okay? And that vector is this green vector here, denoted the gradient of the cost function here that is the discrepancy between what we get and what we want. So it's the gradient of this cost function with respect to this vector. And it's a vector of the same size of xi, and each component indicates by how much the cost would change if we tweaked one of the components, the corresponding component of xi by a tiny amount. So if we have this vector, the question is, what is the value of the vector with respect to the input of that module? And if you know anything about mathematics or engineering, you know that you need to multiply this vector by the Jacobian matrix of that box with respect to its input. But what that means is that you need to know in which way each output of this block would be perturbed if you perturb any input in this block. And those values are collected in a matrix called the Jacobian matrix. And if you multiply this matrix by this vector, you get this green vector here. And that's kind of cool because now you can apply a recursive formula that starts from the top, and then by propagating backwards, you get all the gradients of the cost with respect to all the states of all the blocks in the system. And there's a similar operation that gives you the gradient with respect to the parameters of all those blocks. And so what those give you are the direction and amount by which you should change each of the coefficients in all of those matrices so that the output you get gets closer to the output you want. And a lot of kind of modern software platforms that people use for deep learning kind of implement this automatically. So you write a program that defines the network that computes the output, and automatically you get there's another program that's generated more or less automatically that computes all those gradients for you, so you don't have to worry about it. So it's a bit the magic of deep learning that allows us to kind of come up with all kinds of different architectures. Okay, so that's cool. Then we've got the problem solved. Maybe we can build artificial brains, right? But let's compare brains and computers. So human brain can do on the order of 10 to the 17 operation per second, which means a 1 with 17 zeros behind it. It's got 10 to the 11th neurons, as I said, roughly 100 billion, about 10,000 connections per neuron on average. Each of those synapses can, change state about 100 times per second. Each of those represents more than just one operation, but if you kind of multiply those numbers together, you get 10 to the 17. Now let's take the fastest kind of small enough computers that we can get. This is the Nvidia Titan V Gpu, 10 to the 15 operations per second. So you look at those two numbers and you say, oh my God, this is only 100 times slower. And the power of computers doubles every 18 months. So let's see how long it's going to take for us to get a machine of this size that has the same power as the human brain. It's not entirely true because we probably are off by a factor of about 1,000 here, maybe 10,000. So to have computers of reasonable size that have the power of the human brain, I think we still need to wait a couple decades. So the answer is we're not anywhere near having machines that are as powerful as the human brain. But that's not the main issue. The main issue is that we're nowhere near understanding how to program them, how to even train them, even what the basic principles are for training them. So that's the main question we're facing. We can imagine that one of those GPU cards, which by the way costs $3,000, is very cheap. You can have this in your PC at home. Except you can't get them because everybody buys them for Bitcoin mining. But so there's a shortage. But you could imagine simulating the brain of, say, a mouse or perhaps a rat. Now, I've said a number of times that I would be happy or fulfilled professionally if by the end of my career, which is coming very quickly, I'm afraid, we could build a machine that had as much common sense and intelligence as a rat. And we might have the computing ability for this, but we don't have the underlying principles. That's what we're limited by at the moment. Okay, so let's take another step in biological inspiration, but still sort of trying to understand the principles behind it. So one of the well-known work in neuroscience, so well-known that it actually won a Nobel Prize in the 1970s, but the work was done in the 60s, was about the architecture of the visual cortex. The idea that in the visual cortex you have neurons that look at a small area of the visual field, so they're only influenced by a small piece of the visual field, and they detect very, very simple motifs in your visual field, things like oriented edges. So this was work by Hubel and Wiesel. And they came up with two different concepts, the concept of simple cells that detect those local features and complex cells that basically integrate the activations of multiple simple cells so that if there's a particular motif that appears in your visual field, a simple cell will detect it if it's in a particular location, but a complex cell will activate even if this feature is moved a little bit. And that builds a little bit of sort of distortion and shift invariance in the system. So there was a gentleman by the sweet name of Kunihiko Fukushima, no relation to the nuclear power plant, who came up with a computational model of this idea of simple cell and complex cell, and he stacked multiple layers. But he did this in the early 80s and didn't have really the appropriate learning algorithm that I just described. That's called the gradient backpropagation algorithm. So he used some sort of other unsupervised learning algorithm, which was a little weak. And a few years later, around 1988 or 1989, I was inspired by this and kind of built a neural net that had a little bit of the same architecture, but I trained it using the backpropagation algorithm, and that's what we call convolutional nets. So a convolutional net is a neural network. So here, I'm not drawing all of the neurons and everything, so every pixel of each of these images here that you see is actually the activation of a particular unit in this network. I don't want to call them neurons because they are so simple compared to real neurons that neuroscientists get annoyed when you call them neurons. So I call them units. Each unit here looks at a little patch on the input and computes a weighted sum, compares it to a threshold, and then turns on if it's above a threshold. So that's kind of depicted here. Here is a little patch of coefficients. Here is a patch from the input. You compute the dot product between the vector of those values and the vector of the values here. So basically the weighted sum of those values, where the weights are those values, compare that to a threshold, and then write the result in the output. And then you take the same set of coefficients, shift that window by a little bit, compute the weighted sum again, and that gives you the value in the next pixel over. And again, you take this and you swipe it over the entire input, and you record the results. And basically, every time that the input sort of matches this set of coefficients, you get a highly activated result. And if it doesn't match, then you get kind of a negatively, or you get 0. Or if it kind of anti-matches it, you get a negatively activated unit in this case. This is called a convolutional net because this operation I just described of taking a patch of coefficients and sliding it over an image. That's called a discrete convolution mathematically. And so you take this image, you apply multiple so-called convolution kernels, patches of coefficients here, which will be learned. To this image, you get different feature maps here, which are the detection of different features and different locations on the input. And then you do this pooling operation, which essentially takes the result of this convolution, takes a patch of it, and computes an average of the results, and puts that in the output. But the resolution of those images is half the resolution of the input. So we kind of step the window over which we do this aggregation by 2 pixels instead of just 1. And then repeat the operation. You get, again, convolutions here. So apply windows of weights here to each of those feature maps, combine the result, add up the result, pass through a nonlinearity, and then pool and subsample. And you can do that a few times, and then by the end, you get to some output. What we're going to do is, using backpropagation, we're going to train this network all the way through with a collection of, in this case, handwritten digits to classify handwritten digits. So here is an example of how this works. I'm not sure where the quality is terrible, but those lines here aren't supposed to be there. Anyway, so this is a convolutional net in action, where you see a digit being shifted, and the activations here are shifted but otherwise unchanged. They are the result of applying different coefficients here, different convolution kernels to this input. Then there is pooling, subsampling, convolutions again, pooling, subsampling, convolutions again. And by the time you get to this level, the representation of the input is kind of abstract. You can't really make out what's going on here. And each unit here is essentially influenced by the entire input. And so you get this sort of compression of information and representation of information in ways that may be useful for the classification. So you can build a system for recognizing handwriting out of this. This is one that we built in the mid-90s, roughly, which can not just recognize a single digit, but also recognize multiple digits. That's very important, because what that means is that you can use those systems to recognize multiple objects without having to separate the objects first, which is something that you had to do with the classical methods of the time. And so that turned out to be really important when we started applying those methods to natural images, where you can't always easily separate an object from its background. So here what you have is basically a convolutional net, multiple identical convolutional nets that can look at multiple windows on the input. And what you get here is kind of the best scoring category for each location. And then there is a very simple post-processing that kind of picks out the correct interpretation of this whole scene. Here's a younger version of myself putting a piece of paper under a camera and hitting a key. This is my phone number in Holmdel, New Jersey at Bell Labs, no longer operating. This is from 1992, roughly. And in just a few seconds, the system could process the image, recognize the characters, and do a pretty good job, even on kind of small handwritten digits in various styles. Could deal with European style, which with very few training samples. All kinds of weirdly drawn characters like that. And to be able to run this at sufficient speed, we had to run on a special hardware called the DSP32C, which was capable of the incredible speed of 20 megaflops. This is Donnie Henderson, who was a lab engineer, and Rich Howard, who was the lab director at the time. Eventually, we built a system to actually recognize checks. And this system was deployed around 1996. And by the end of the 90s, it was reading something like 10 to 20% of all the checks in the US. So if you're old enough, chances are maybe one of those systems read your checks. If you deposited a check at an ATM machine in the late 90s, early 2000s, chances are the system that was actually reading the amount on your check was one of those. So quite successful. But by the mid-90s, the interest of the machine learning community in neural nets died. And it's not entirely clear why. I think sociologists of science will have to figure this out. But what happened probably is that those systems required a lot of investment to develop the software to make them run, and a lot of kind of intuition of how to make them work and experimentation. And this was before the days of MATLAB, before the days of open source software, before the days of Linux. Before the days where companies like AT&T were ready to distribute software in open source. And this was before the days where we had fast computers and large data sets with which to train those things on. So those things were working really well on handwriting recognition, slightly less well on speech, but okay. But they required very large data sets to be trained. And we just didn't have a lot of applications for which we could get a lot of data. So that limited the applicability. And the machine learning community kind of moved away from it. There's a phenomenon I think that's interesting also, which is one reason the community, and because there are mathematicians in the room, I have to say this, because there was a lot of mysteries about why those things were working that were really not understood mathematically, whereas simpler models that people got more interested in between the mid-90s and mid-2000s were much better understood mathematically. And the academic research community likes to understand stuff that they do. They don't like things they don't completely understand, because you can write papers about stuff you understand, you can write theorems. Those things are messy, and you couldn't do that. And so despite the fact that they were working, they were semi-abandoned. But some of us really knew that eventually they'll come back, because there were situations where they were obviously superior. And the reason they were superior is that those things could learn not just to recognize kind of simpler machine learning techniques, but they could learn to represent the world. So they don't just learn a classification, they learn to kind of figure out what are the essential parts of an object and how those parts assemble to form objects. And so they were doing something a little more powerful, which is why they required more data. So I kind of stopped working on this for a few years. Between roughly 1996 and 2002, I kind of did something else, worked on image compression, because there was no interest from the community. And in 2003, I kind of restarted seriously working on this and did this little experiment where we had this little radio-controlled truck with 2 cameras on it. And what we did was have this truck driven by a person. And the person was instructed to drive the truck straight until the truck was about 2 meters away from an obstacle, and then we'd have to either turn left or right to avoid the obstacle. And then we trained the convolutional net to look at the 2 images from the 2 cameras, and then train the convolutional net to predict the steering angle of the human driver. Very simple. With about 20 minutes of training data, the system was able to do a decent job at driving itself. And that's what you see here on the left. So this is the robot driving itself from its point of view, first-person point of view, if you want, where it's able to navigate this busy New Jersey backyard here, a cluttered New Jersey backyard, and this smudge on the camera window and everything, and it deals with this. The transmission of the video is bad quality because it's analog video, but it's still able to drive itself. So we showed this to a bunch of people at DARPA, and they said, oh, that sounds great. We should have a DARPA program to have robots drive themselves using machine learning. And they started a program called LAGGER, Learning Applied to Ground Robots, $50 million dollar project, which where those little robots here were fitted with 4 cameras, and had 3 computers in the belly, and were supposed to drive themselves in nature. So this is not for on-road driving, but for off-road driving. What we did was take a convolutional net and basically train it to tell us for every region in the image whether that particular region in the image corresponds to something the robot can drive over, whether it's kind of flat or whether it's an obstacle. So you can do this with classical vision technique using stereo vision. So this is an example here where with stereo vision you can figure out if a particular pixel sticks out of the ground, and so you can label it red in this case. The problem is that stereo vision is first quite expensive, and second only works to a limited range, about 10 meters in this case. So we couldn't use this for kind of navigating in a long distance. So we used, though, the data produced by stereo to train the convolutional net to label the entire image, and that's the kind of result we got. So the network tells us there is this path here, and you can drive all the way through, or there's this little passageway here that you can drive through behind those hedgerows. So that was the convolutional net that was used. It was looking at kind of bands around the horizon. And then, once you get a labeling from the neural net, you can put this in a map. And then if there's a goal to which the robot is supposed to drive, you can do kind of planning in this map to kind of avoid all the areas you don't know, or the dangerous ones, or the obstacles, and then let the robot drive around. The robot actually has multiple vision systems. It has one that runs at high speed to avoid unexpected obstacles when it turns around. And it's got the neural net that runs at about 1 frame per second that does kind of long-range vision if you want. So think of yourself kind of, walking around. So here's a little video of this system. This is accelerated twice. And those are 2 PhD students who are being very annoying to this poor robot. But they're entitled to be annoying. They also are pretty sure the robot is not going to break their legs because they actually wrote the code. This was Pierre Sermanet, who is now at Google, working on robotics, Google Brain in California. And the other person was Raya Hadsel, and she leads the robotics research group at DeepMind in London. So pretty soon we realized that we could not just label a region or a pixel as to whether it's traversable or not, but more interestingly, with the category of the object the pixel belongs to. So for example, here is an image. It would be nice to know that all of this is road, and those are cars, and those are buildings and windows, and those are trees, and that's the sky, etc., and sidewalk and pedestrians. And we actually managed to do this. If my computer wants to switch to the next slide, which would be nice. Oh. It switched 2 slides, which I don't like. Okay, it refuses to show you this video for some reason. Okay, so maybe I'm not going to show you that video. So what you would have seen is an animated version of the, oh, here we go, okay. So this actually, we could run this at roughly real time, about 20 frames per second. This is actually not on a car, but on a bike. So this is someone kind of riding a bike down a street in Greenwich Village. And the system is very far from perfect. It says that this is a desert or sand, and that's the middle. This is the middle of Manhattan. There's no beach I'm aware of. Certainly not desertic. So, but it detects NYU students very well, and vegetation and etc. So at the time, this was really state of the art. It worked as well. It was even running on a regular computer. It was about 100 times faster than the best competition. Sort of alternative technique using kind of more classical computer vision methods. And we had this special piece of hardware running on what's called an FPGA, kind of a programmable hardware, if you want, that could run at about 20 frames per second. So that actually inspired a bunch of people to say, well, maybe we can use this for self-driving cars. So 2 companies picked this up quite quickly around 2014. One is Mobileye. So this is a company, an Israeli company founded by Amnon Shashua, who's a professor at Hebrew University. And they switched to using convolutional net around 2014 and started using this kind of semantic segmentation type applications there. And another company that started using this is Nvidia. So the company that makes the graphical processing units are used for gaming, but they are the ones that we use also to train those neural nets. I'll come back to that in a minute. So what happened in 2012, so all of this was kind of a little under the radar until about 2010, 11, 12, where in 2011 there were breakthroughs in speech recognition using deep learning that started to attract the attention of the speech recognition community. And at the end of 2012, there was a competition called the ImageNet competition. So it's a data set of 1.3 million images with objects from 1,000 categories. And the best error rate on this data set was around 26% with sort of more classical computer vision techniques. And a large convolutional net implemented by our friends at University of Toronto, they were the first to have a really efficient implementation on GPU of those very large convolutional nets, got something like 15% error by some measure of performance. So this was almost half the error rate that previous methods had. And all of a sudden, the computer vision community switched to using those techniques. The revolution occurred in a very short amount of time. I've never seen this happen before, where an entire community shifts from one set of techniques to another. In fact, in 2011, we submitted our paper on the semantic segmentation technique to CVPR, the big computer vision conference. And the paper was rejected, even though it was beating records, et cetera, because basically people didn't know what convolutional nets were and did not believe that a method they never heard of could actually work so well. So they assumed there was foul play or something. 3 years later, you cannot get a paper accepted at CVPR unless you use convolutional nets, which actually is not good because it kind of kills diversity a little bit. But that kind of gives you an indication of how big this revolution was. And so those networks end up being very large, having tens of millions of coefficients of knobs, millions of units and weights. And they learn to detect very interesting features on their first layer. So these are the set of coefficients on the first layer kind of depicted in a kind of pictorial fashion. So they indicate basically the motif on the input image, kind of little patches of images that would activate each of those units. Each of those corresponds to a feature map, a unique category. And there's one feature map that detects horizontal edges, another one that detects slanted edges or slanted gradings, et cetera. So those are things you would hardwire into a vision system if you were to design it by hand. And over the last few years, what we've seen is an inflation of the number of layers in those networks. So this is kind of the favorite architecture for this ImageNet competition, circa 2013, and then 2014, and then 2015. This one has 50 layers. And this one has even more. These are the ones that are used in practice for recognizing images at Facebook, for example. So Facebook users upload, there's 2.1 billion users at Facebook, roughly. And Facebook users upload on the order of 2 billion photos every day. And each of those 2 billion photos goes through 4 convolutional nets. So there's one that basically detects objectionable content, things like violence, pornography, things like that. There's one that labels the image and produces captions that are useful for the visually impaired. So the visually impaired get an idea of what is in a picture on Facebook using this text description. There's another one that essentially tags the image with all kinds of different categories and objects, et cetera, which is good for figuring out if Facebook wants to show you a picture because it matches your interest. So let's say you're interested in sailing. It's a beautiful picture of one of your friend's sailboats. And Facebook knows you're interested in sailing. It's going to show you this picture. If the same friend shows you, uploads a picture of his cat, maybe you're not so interested in cats. We're not going to show that to you. And then the last one, which is only activated in certain countries, does automatic tagging of faces. So if you take a picture of your friends and you upload it, your friends are alerted that a picture of them is there and they can be tagged in the photo automatically. So why is it that we need layers? Why is it that we need this kind of weird, funny architecture? And there is a lot of interesting theory to do about this. In fact, some people, perhaps in this audience, I'm not sure if they're here, who have worked on the theory behind convolutional nets. So kind of trying to derive convolutional nets from first principles. We were kind of dreaming this up from biology, but in fact, you can actually derive why this is a good idea. And so Stéphane Malin has been working on this, and he's here at IPAM. I don't know if he's in the room here, but Johan Brunard, his student who is now at NYU, has been working on this also during his PhD and kind of kept working on this. Mark Taggart, who used to be at IPAM, also worked on this. So there's a number of interesting work there on the kind of theoretical justification of those architectures. And I found that absolutely fascinating. And I think IPAM, I should thank IPAM for this because that's really where it happened. Why is it that we need those layers? Why is it that the low-level feature detectors are edges, and then those are assembled to kind of form slightly more abstract concepts like corners and circles and things like this. And those are, combinations of those are detected to form kind of parts of objects, et cetera, et cetera. And it's because the world itself is compositional. The perceptual world in particular is compositional. So, but the world in general, physicists will tell you, right, there is elementary particles and they assemble to form less elementary particles, and those assemble to form atoms and then molecules and then materials and then objects, etc. Right? So there's kind of the same phenomenon in the perceptual world where you have pixels, and pixels assemble to form motifs, and motifs assemble to form slightly more complex features and parts of objects and scenes, etc. And you have this same kind of hierarchy in text with characters, words, clauses, sentences, paragraphs, etc. In audio, in basically every natural signal has a compositional structure, which makes it amenable to representation by those hierarchical systems. So it sounds like a conspiracy, right? I think Einstein said the most incomprehensible thing about the world is that the world is comprehensible, and because among all the possible input-output functions, why is it that the ones that we are interested in computing are easily representable by these kind of multi-layer architectures that our brains can understand, our machines can understand? There's many, many, many more functions. Most of them are completely random, and there's no way in hell that we can compute them. But they don't seem to matter to us in the world. Or maybe they do, but we don't realize it because we have no idea what they are. So that's kind of an interesting philosophical question, or mathematical question. So what's happened over the last few years is that there's been a huge amount of effort by various companies, Facebook, Google, Amazon, Baidu, Microsoft, IBM, everyone really, to kind of make those techniques useful and scalable. And what we can do now is train one of those convolutional nets in about an hour on a network of 256 GPUs. Takes about an hour to reach kind of state-of-the-art performance on the ImageNet dataset. But here is the state-of-the-art in computer vision now. I'm not going to go into the technical details, but this is the result produced by a system produced at Facebook AI Research in Menlo Park called Mask RCNN. And the code for this is open source. Actually, it's a part of a package called Detectron. It's kind of inspired by Perceptron a little bit. And what this system can do is not just recognize an object in an image, but also put a bounding box around it and even kind of draw an outline of the object, even if you only see the kind of a partial, the object partially, and even if there are multiple overlapping objects of the same type, like all those people, for example, are kind of delineated. The baseball bats, the dog, the wine glasses, the wine bottle, the computer in the back, the backpacks, the umbrellas, the sheeps. You can count sheeps. There's always a picture with sheeps in those computer vision things. Cars, etc. It's pretty amazing how it works. If you would have asked a computer vision scientist only 5 years ago, how long is it going to take for us to be able to do this to that level of accuracy, and they would have said maybe 10, 15 years. We don't know. So that's pretty amazing. You can track body pose. And etc. You can recognize 3D objects. In fact, we had a talk today at the IPAM workshop on the very topic of recognizing 3D objects. But the amazing thing is that you can use those convolutional nets for all kinds of stuff. You can use them also for translation, and that has nothing to do with computer vision. So in fact, how can you use this for translation? Well, you can have an input sentence. For example, you want to translate French from, or I guess here it's English into German. You have an English sentence that goes through a convolutional net. It's actually a gated convolutional net, which is slightly more complicated. And it goes through kind of a few things that are a little more complicated that I'm not going to go into. And this thing kind of produces one word at a time and kind of takes into account the previous word. It's produced in German, and it kind of transforms a sequence of symbols into another sequence of symbols. But internally, it's basically a convolutional net, or two convolutional nets. So that's kind of it's kind of interesting. It's very useful, of course, for Facebook, that translates posts from people. Now, one thing we do at Facebook is that we distribute a lot of our code in open source. So a lot of this stuff that I talked about today, you can actually just download the code and run it if you have a GPU. And you can play with the tools that we use for training deep learning systems. There's one that we like called PyTorch that we've contributed a lot to. And there's the number of applications of deep learning and convolutional nets and other deep learning systems pop up every day. Things like, I mentioned self-driving cars. There is medical imaging. There is genomics. This is interesting work by University of Toronto a couple of years ago of kind of using convolutional nets to emulate the sort of biochemical machinery that kind of translates DNA, if you want, and figures out parts of the DNA that are expressed. Image restoration, it's used in science, particularly in high-energy physics. There's a lot of interest there, in astronomy as well. And new applications pop up every day. And this is going to change lives. It's just going to change society when we have self-driving cars around. They're going to use deep learning. They're going to use convolutional nets to do vision. They already do, actually. If you are lucky enough to drive a Tesla, the vision system that drives the Tesla on the highway, that's a convolutional net. I mean, it uses a convolutional net. There's really good results now in medical imaging for cancer detection, for melanoma detection, for games, for translation, virtual assistant, etc. Here's a small video. This is a self-driving car system developed by friends at Nvidia. And here it's accelerated, but it drives this car around completely by itself. The person here is not touching the wheel. It stops at the intersections, and it looks around. And it's not cheating in the sense that it's only using a camera. And you see the convolutional net here producing a kind of guess as to where the car should turn and what trajectory it should follow. And it's country road without markings, etc. I think the person here controls the speed for stopping at a stop sign, because I don't think the system actually detects a stop sign yet. But it works pretty well. I mean, that's actually the easy part. So again, that's basically a convolutional net that has been watching a human driver drive for several thousand hours, and with a few tricks. Interestingly, those guys, actually, that group is in New Jersey, in the building in Homedale that used to be the Bell Labs building where I used to work. And these guys used to be my colleagues there. So, I don't know, the history has this kind of weird full circle thing. This, slightly more general approaches to deep learning. So, one of the topics of the workshop that is taking place this week at IPAM is kind of new methods in deep learning. So things where we can apply deep learning that are not sort of classical types of data. So for example, it would be very interesting to be able to apply deep learning methods, convolutional nets in particular, to data that comes to you in the form of a function on a graph, for example. And it's not obvious how to do this, and there's a lot of people in this room working on this, but I think it's absolutely fascinating. Another extension is the ability, kind of using deep learning systems that will have the ability not just to perceive, but also to reason. So for example, let's say I have this kind of problem here where I have an image of this type, and I ask the question, is there a matte cube that has the same size as the red metal object? And so, you kind of have to look for it. You kind of have to think about it and sort of, count how many objects there are. So things like this. Are there more cubes than yellow things, okay, in this image? And so what you have to do, of course, is kind of, count the number of cubes, count the yellow things, and then figure out which one is largest and give you the answer. So you could think of a sort of neural net, if you want, that would have operators of this type. So a convolutional net that produces features, and then you have another module here that counts that filters objects that are yellow, and then filters objects that are cubes, and then another module that counts how many of those there are, and another one that compares the two, and then that gives you the answer. The problem, of course, is that this particular neural net will have to change depending on the input. And so what you have here is a new kind of neural net, which is sort of dynamic. The input determines the architecture of the neural net, the architecture of this graph of modules that is going to compute the output. But the beauty of it is that you take this sequence of words, you run it through a particular type of neural net, and then you run it through another type of neural net that produces a representation of this graph of operators, and then you run the image through this operator, and it gives you the answer. If it doesn't give you the answer, you backpropagate gradient through this entire thing, so that eventually not only the network produces the right answer, but those modules actually compute the right function, and their arrangement is correct. And the amazing thing is that this works. This was a project at Facebook AI Research. The first author is Justin Johnson, who's a PhD student at Stanford. There are other, so the important thing here is that the network is dynamic. The structure of it is dynamic. There's a very interesting set of development also called memory augmented neural nets. So these are neural nets where you have this neural net and it's augmented with a piece of soft circuit, if you want, that is to be used as a memory. And there's several names for those things: memory networks, stack augmented recurrent nets, neural Turing machine, differentiable neural computers. There's sort of a lot of work on this at Facebook, at DeepMind, and various other places, at Microsoft. And there's different architectures of this type, with which I'm not going to go into the details of. But basically, they are based on many of them are based on the idea that you can build a memory, kind of like a RAM, if you want, but you make it differentiable so that it can be integrated in a neural net and then trained to essentially store whatever is required for a particular task. And the idea came up a few years ago, and it's been a big boon particularly for people working on natural language processing and kind of reasoning, things like that. So this is an old example, but it's kind of fun. Unfortunately, you can't read that very well. But this is a short, abstract version of Lord of the Rings. So there's Bilbo traveled to the cave. Gollum dropped the ring there. Bilbo took the ring. Bilbo went back to the Shire. Things like that, right? 15-sentence version of Lord of the Rings. That's about everything that actually occurs in Lord of the Rings. And then at the end, you can ask the system a question: where is the ring? And the system has to have understood the text and kind of have some representation of where the ring actually is. And those memory networks can actually do this. They can answer this kind of question. In fact, there's a whole bunch of different types of questions that those things can do, including things that require a little bit of inference. Even if this inference kind of looks funny here. So for example, Brian is a lion, Julius is a lion, Julius is white, Bernard is green, what color is Brian? So if you do a little bit of kind of overgeneralization, you can say all lions are white, and you answer white. And that's what the system does. It's not, mathematically correct. This is a joke about, cows that are black and white. So that led me to disclaim that deep learning is dead. And the new thing is called differentiable programming. So essentially, what you do is you write a program that generates a compute graph. The program can be turned into a graph of operators. And because of this automatic differentiation trick, you can automatically generate another program that will compute the gradient of the output of this first program with respect to all of its internal parameters. And that allows you to essentially train the program to do a particular function. So let's call that differentiable programming. And it's kind of a new paradigm for programming, really, that kind of, brings machine learning or deep learning and programming together. There's a slightly different, although very similar concept called probabilistic programming. So it's the same thing, except that the variables that are manipulated are not vectors, but they are kind of distributions of, distributions, probability distributions. Makes it a little more complicated. So, okay. Let me skip ahead now. I probably don't have much time left, right? Probably none, actually. Who's running? 5 minutes. Okay, so obstacles to AI. Here's the problem. All of those things that you've seen here, this is not real AI. We can train machines to accomplish particular tasks that are very narrow, but we can't train them to do things that are very general. So none of those machines has general intelligence. None of those things has common sense. And of course, common sense has been kind of a red herring in artificial intelligence for many decades. And the question is, we don't even know what common sense is. So I have a hypothesis, working hypothesis, which is common sense is our ability to fill in the blanks. So we can predict the future from the past to some extent, right? In fact, in my opinion, the essence of intelligence is the ability to predict, or the ability to fill in the blanks. Right now, you're seeing the front of my head, but you can probably figure out more or less, even if you've never seen it, what the back looks like, because you have a good model of what a face looks like. If you face a situation in a room, you can infer to some extent what happened in that room before. It's very useful if you are a police inspector. So there is, this ability to basically fill in all the information that we don't yet have, and that's kind of the essence of intelligence, or an important component of it. So perhaps finding a way to train machines so that they could fill in the blanks automatically by just observing the world would be kind of a way to make significant progress in AI. And we could call this predictive learning. In fact, that's a little too generic. So maybe something like imputative learning, but that's kind of too pedantic. So I don't know exactly how to call it, but something like that. And babies do this. And babies learn a lot of things by observation. They learn object permanence, after that age. So the fact that an object, still exists even if you don't see it. You learn this by the age of 3 months, roughly. Orangutans are almost as smart as we are. This is a baby orangutan. He's being played a magic trick here. And, he's looking inside of this cup, and there's supposed to be an object, and the object is not there, and he's rolling on the floor laughing. What's interesting is that orangutans are essentially as smart as we are. They're not going to win field medals or anything, but they're very close in terms of intelligence. They're not social animals. They basically do not interact with other animals of their kind, except the kind of mother-child relationship. Which means that intelligence is not necessarily linked to language. Language might be kind of an epiphenomenon, if you want. I get NLP researchers very upset when I say that. So how do babies learn? So if you show a baby before the age of 6 months, a situation like this, where you push a little cart off of a support and the cart doesn't fall, of course there's a trick, right? It's held behind. Before 6 months, they say, yeah, sure, that's the way the world works, no problem. After 8 months, they go like this. And you can tell, right? That's how psychologists actually measure whether a baby has kind of absorbed a particular concept. So between the age of 6 and 8 months, they kind of build this model of the world that allows them to figure out that an object just doesn't stay in the air if it's not supported. It's going to fall, right? So gravity and conservation of momentum and things like this, that pops up around 6 to 8 months. In fact, there was this chart that was put together by Emmanuel Dupuy in Paris that says things like object permanence pops up at 2 months. Animate and inanimate object, the difference between the two pops up around 3 months. Sort of natural categories, stability and support, and gravity, inertia, conservation of momentum, that's about 7 or 8 months, etc. And there's whole charts of this for linguistic and social interaction. Now, how do babies learn this? By observation. Babies are kind of helpless in terms of motor control, so they don't interact with the world very much. They just observe, and they get all that stuff, right? They figure this out. We don't know how to train machines to learn about intuitive physics. And we need to. So there's really 3 types of learning. Supervised learning, I told you about. This is the scenario that I described, where you tell the machine what the correct answer is. There's another mode of learning called reinforcement learning, where you don't tell the machine what the correct answer is. You only tell it whenever it does good or it does bad, right? So it's kind of like training a pet to do a trick, right? You wait for the pet to do the right thing, and then you give it a reward. That's very useful for games. So if you've heard of AlphaGo and AlphaGo Zero from our friends at DeepMind, it's trained using a form of reinforcement learning. So the system plays millions and millions of games of Go or chess against itself, and then sort of compile the winning strategies, if you want, in a neural net that basically learns, which move to play given a particular situation, and kind of produce a probability distribution over possible moves, and explores a huge amount of that space in a relatively short time, and after having played a few million games, plays better than the world champion by a large margin. So that works really well for game because you can run the games millions of times. But you can't run the real time millions of times, the real world millions of times. If you want a machine to learn to drive, it will have to run off a cliff 50,000 times before it figures out that it shouldn't run off a cliff and how to not run off a cliff. I apologize for the quality of the animation. I'm not sure what's going on. So that led me to this slightly obnoxious analogy, which is that in terms of the amount of information you ask the machine to predict at every cycle, every time it perceives something, this kind of predictive type of learning where you ask it to predict everything, essentially, like the entire future, for example, there's a huge amount of information the system has to predict. For supervised learning, there's a kind of small amount of information you ask it to predict. This is what's provided by a person, and that's kind of the icing on the cake in terms of volume, if you want. And then reinforcement learning, you're only telling the machine you did good, you did bad, and the machine really can't learn anything this way without millions of trials, and so that's kind of the cherry on the cake. And that's become a bit of a meme in machine learning. People make fun of me with this, and so I have to show it every time. So reinforcement learning works well for game, for Go, for Doom. This is actually a Doom player that was built at Facebook that kind of won the Doom competition in 2 years in a row. Actually, it's 2 different systems. It works for StarCraft, although not well. We're still working on this. But there's this idea somehow that unsupervised learning will help us make progress in AI, and the next revolution in AI will not be supervised. I stole the concept of this slide from Alicia Ayfors from Berkeley. Okay, so I'm completely out of time, so I'm going to jump to something, the last thing I want to talk about, which is, and this I wasn't going to talk about in the first place anyway, which is unsupervised learning, and particularly predictive learning. So the big problem we have now with AI is how do we get machines to learn models of the world, predictive models of the world. So if you can probably predict what's going to happen if I push this microphone a little too far, right? Not only can you predict it's going to fall, but you can probably predict it's going to make a horrible noise. So you have a model of the world that is formed by your experience, and you can configure your frontal cortex to basically predict a situation in any new situation you are. That's what's missing from AI systems today, and that's a very, very important component of AI systems. As I said, the essence of intelligence is the ability to predict. So there is this concept called adversarial training, which I'm going to go to in just a minute, and the basic problem is that the world is essentially unpredictable. If I do this experiment, I put a pen on the table, and I lift my finger, and I ask the system what's going to happen next. The system can predict that the pen is going to fall if I show it enough examples, but it can't probably predict exactly in which direction it's going to fall. So if I want to train a predictor, looking at the past, I ask it to predict the future, and it's going to source of random numbers. It can predict a particular point, which is a plausible future, but perhaps the future that will occur is another point on this kind of surface of potential plausible futures. And I don't want to punish the machine for having made the wrong prediction, because there's no way you could have made the right prediction. So I need the machine to be able to predict either a distribution of that shape, or if it predicts a single point, to tell it that it shouldn't be punished for predicting the wrong point on this manifold. The thing is, I have no idea what this manifold looks like. So what we're going to do is we're going to train a second neural net to learn what this manifold looks like. And so there's 2 neural nets we're going to train, one to predict, the other one to tell the first one whether what it predicted was good or bad. In other words, whether its prediction was on this surface of potential futures or not. And that's the idea of adversarial training. And since I'm out of time, I'm not going to go into the details, but essentially you show a small segment of video to the machine, and then you show it the actual future, and you train a neural net to tell that's real. And then you make a predictor, predict what the future is, and initially the predictor is terrible, and you train the second neural net called the discriminator to tell it that this is fake. Okay, so produce a large value here, produce a small value there. And you can represent this by the surface, where this is the real futures, and these are kind of predicted fake futures. And after a while, when you train the discriminator, it's going to be able to tell the difference between fake and real. But then this guy is going to train itself, is going to use the gradient of the output of the discriminator with respect to its input, and is going to train itself to produce an output that this guy can't tell the difference, can't tell is fake. And so eventually the green points produced by the discriminator are going to be such that this guy can't tell the difference. And this thing works amazingly well. You can train it to generate random pictures of, you train it on bedrooms, and then it generates bedrooms. Those are fake bedrooms. Random numbers in, reverse convolutional net, deconvolutional net, and bedrooms out, and those are non-existing bedrooms. And they have everything you need for a bedroom. You can generate faces, you can generate funny images like this that don't look like anything. They're kind of like abstract paintings. They're trained on natural images. You can train them on dogs, and that generates kind of soft dogs. This is our Salvador Dali kind of network. You can train it to do video prediction. So this is really what's interesting if you want the machine to learn to predict. So that's if you use kind of a classical algorithm to train a system to predict the future, and it predicts blurry futures because it doesn't know what the future is going to be, so it predicts the average of all the possible futures, and that's a blurry image. If you use those techniques, then it predicts, pretty nice futures. So the first 4 frames of each of those clips is observed, and the last 2 frames, indicated by the red contour here, are predicted. And the things kind of continue moving in the direction they're supposed to move. Here, the system invents how this bookcase is supposed to look. It has never seen this apartment before, but as the camera rotates, it says, well, this is a bookcase, and the rest has to look like a bookcase. This is a couch, the rest has to look like a couch. And if you apply this to images coming from a car, for example, where these are not pixels, these are kind of labeled images, it predicts that pedestrians who start crossing the street are going to keep crossing the street. Cars that start turning left are going to keep turning left, and the scenery is going to keep moving around. And so you'd like to be able to predict what the other people on the streets are doing to be able to drive. So the ability to predict, again, is going to be an important component of self-driving cars. I'm going to thank you very much for your attention and stop here, and it was a pleasure.
Thank you very much. We have time for a few questions, so I'm going to try to take this mic down, and also Stacy has a portable mic. So if anybody has a question, please raise your hand. We'll try to get the mic over to you in some way. Oh, no, this won't go far enough. Anybody? Yes.
You've shown very beautiful applications and the scenarios. What will be the limits of these neural networks and artificial intelligence?
Yeah, the limits of artificial intelligence. So I don't see any limits to artificial intelligence except theoretical limits of what computation can do. So there are problems that are, that don't even accept approximate solutions in a reasonable amount of complexity. So those would be outside of the possibilities. But I don't see any limitation in terms, I don't think human intelligence is an upper limit on the intelligence of machines that we're going to build. At some point, we're going to figure out how to make machines that are more intelligent than humans. Now, current methods are very limited for the reason I mentioned. We can do supervised learning, we can do reinforcement learning, but we don't have those techniques yet, except perhaps those kind of adversarial training techniques to train a machine to, learn models of the world, predictive models of the world. That would be kind of an essential component of an AI system that is autonomous. I mean, there are other problems that we haven't solved, but that's, in my opinion, the biggest obstacle at the moment. And so this is the first mountain that we see on the road to human-level general intelligence. And we don't know how many mountains are behind it, right? There might be a whole bunch. So it could take 30 years. It could take 50 years, 100 years. We have no idea.
Any other questions? So we're training a neural net to predict questions now.
Okay.
So the last 2 will be auto-generated, I think.
So if there are no limits to artificial intelligence, what about semantics? John Searle's old critique. I don't know if that's outdated now, or Hubert Dreyfus's concern about
Right. So
machines still can't do? Do you see that like as breaking through past syntaxis semantics?
no, I think this is actually okay. So there's a bunch of questions in philosophy about consciousness, qualia, like how do you explain your experience of the color blue, for example, right? And various things like this. I think those are non-questions. I think those are questions that will disappear. They're kind of like, in the 18th century, people were completely puzzled by the fact that, they understood how the eye worked, and so they figured out that the image in the retina forms upside down. And the immediate question was, why do we see right side up? And, if you know how, processing works behind it, the question makes no sense, right? I mean, it doesn't care, whether it's... So I think, those questions are of a similar nature. I think the Chinese room argument, which is John Searle's argument, is a stupid one. I think he just died, so it's okay. But, and so I'm not worried about this at all.
Yeah.
Hi. I just wonder, how do you think about the Hinton talk about the capsule?
Uh-huh.
He said that neuron is not a good idea. It's maybe the future is a capsule. Did you agree his opinion?
Well, capsules are not very different from convolutional nets. They are a type of convolutional net where the pooling unit is of a particular type that essentially combines coordinates, if you want, of the parts that form a bigger part. And so I view it as sort of an enhancement or a specialization of convolutional nets. The advantage of it is that you can train them to recognize simple objects with more invariance and fewer samples than traditional convolutional nets. So they save you samples. I don't think they will change radically the way we do things. I think it's a cool idea. I mean, there are a few architectural ideas like this that came up in the last few years, like the idea of attention or gating, which are used for a lot of natural language understanding systems, and capsules are of that type. So there's a lot of ideas of this type I think are very interesting. It's not like all of a sudden neural nets are obsolete. It's just it's a particular type of operations that you put in a neural net.
All right, so thank you all very much for coming. There'll be the second lecture of Yann tomorrow, and we hope to see you all there. Thank you so much.